Hi, AP Chemistry. I am out of town this week at a family function. And so, what we're going to do, because it's the first week of the third trimester and we're done learning new stuff. And so, this week we're going to start reviewing. And because I'm not here, we are going to start reviewing by doing big idea number 4. Now, big idea number 4 is not actually the easiest big idea, but it it's the shortest, and so it's a good thing to do when I'm not here. And the reason why I had you keep all your tests is because the best way to kind of get these ideas back in your mind, because retention rates drop off over time, is to just work your old tests. Now, how this is going to go, these are how you're going to be graded this trimester, is that we're going to go over your old test, and then I've also written a new test. Actually didn't write it, but I compiled it from online, from some of the AP chemistry review books. And so I'm going to go over your old test, and then I'm going to assign the AP review tests, and then we're going to do, so anyways, it's the first one. But the first thing we're going to do every week, or ever so often when we review, is go over the old tests. And so it's been a while, so you guys have your tests, you have answers on them. Let's just take a minute, not a minute, let's take a class period and talk about these tests. So in a series of experimental trials on a reaction between substances A and B, the concentration of B was held constant and A was doubled. It was found that the rate did not change. The reaction rate did not change. What is the order of the reaction with respect to A? Now, when you guys actually took this, I noticed that you guys were almost paralyzed. There were too many words. So let's pull this apart. There is a series of experimental trials on substances A and B. So A and B are the reactants, and they're making something. Let's just say AB. Then it says the concentration of B between the trials. So you got the concentration of A, you got the concentration of B, we got trial 1, we got trial 2, and it says it was found, okay, so the concentration of B was held constant. So between trial 1 and 2, there was no change. And between trial 1 and 2, let's say the concentration of A doubled. Then it says it was found that the reaction rate did not change. So the rate had no change. Now think about this. You doubled A, you left B alone, and the rate didn't change. What that means in kinetics is A must not affect the rate of the reaction. And so the order of the reaction with respect to A is 0 order, because you doubled the concentration of A and the rate didn't double. That's what happened if it was first order, or it would have quadrupled if it was second order. All right, so then moving up here, now I always have to erase because no, you guys, I know you by hell. Slow I erase. So in this reaction, the rate law is K equals, so the rate law is K equals, there's only one reactant, it's AB2. It's nothing there, so it must be 0, because anything to the 0 power is 1. So what is the order of AB2? It is A. We got 2 0 orders in a row. The rate of any chemical reaction can be determined from its balance equation. Nope. The rate is determined from the sum of the elementary steps up through the slowest step. Is it determined from the fastest step in the mechanism? No, it's determined from the slowest step in the mechanism. Is it measured in liters per second squared? No. Is it measured in degrees Celsius? No. Is it determined by the rate of the appearance of product? Yes. Now here's why. When you guys were learning this the first time, we said that you can monitor the rate of a reaction this one you could do one of 4 ways. You could monitor how fast A is disappearing, or how fast B is disappearing, because the reactants disappear as the reaction proceeds. Or you could measure how fast C is appearing, or how fast D is appearing. Because as a reaction progresses, in the beginning you have all reactant, no products. At the end you have all products, no reactants. So as the reaction proceeds, are disappearing, and the A and B, the reactants, are disappearing, and C and D are appearing. So when it says determined by the rate of the appearance of products, yes, the products are appearing, the reactants are disappearing. All right, so then next question. Now guys, when you take your test on this, your only grade this try is going to be based on a little tiny quiz, little tiny quizzes about each big idea. And so, all right, so now what do I do? Oops, remember, now I'm not so good at this. I have to walk over to the, all right, I think I'm on 4. Okay, in collision theory, an effective collision depends on, okay, there's 2 things. Remember this reaction mechanism? So when 2 reactants collide into each other to make a product, they have to A, hit with enough energy, hit with enough energy to get over the hump. I call this hump activation energy. So if 2 reactants run into each other and they're going fast, but they're not going fast enough, they run into each other, they come up here, but they don't turn into products because they can't get over the hump. And sometimes there's some reactions where they have to be aligned perfectly, that they have to bump in exactly the right orientation. And so in collision theory, an effective collision has 2 parts. The 2 reactants have to be lined up appropriately, because remember, the reactant bonds break and the product bonds formed. And not only do they have to hit in the right orientation, but they have to hit with enough energy to overcome the activation energy. And so when you look at this, the best answer is D, that they collide energetically. That means enough energy to get over the activation energy, and they have the right orientation. Now, molecules collide energetically with the container walls. That has nothing to do with it. We're talking about how reactants run into each other and their bonds break and then products are formed. It doesn't have anything to do with the container walls. It's okay, they need to collide with the right orientation, but they still, if they have the right orientation but they can't get over the hump, it's not an effective collision, it's an ineffective collision. No, some reactants aren't gases. There's also solids, liquids, and aqueous. And then they don't necessarily have to be at room temperature. Obviously, as the temperature goes up, they have more energy. One of the ways to speed up a reaction is to make it heat it. So it doesn't, all the other things are distractors. A series of steps from the beginning to the end of the reaction is the reaction mechanism. Now, the reaction mechanism is the sum of all the elementary steps. So step 1, step 2, step 3 are called the elementary steps. The reaction mechanism is all of them together. The rate determining step is part of the reaction mechanism, but it's the slowest step. Catalysis, all a catalyst does, you're going to find out later, is lower the activation energy, so you have more effective collisions because it's easier to get over the hump. And totally lost my train of thought. I'm sorry. So you have more effective collisions. It's easier to get over the hump when you have a catalyst. And then intermediate steps are, I don't even know what that is, but it's B, reaction mechanism. In the reaction, oh, I love this. Guys, this is key. You saw this on a couple free response Fridays. At any given time in a reaction, if you know the rate of one of the substances, products or reactants, and you know the stoichiometry, you can get the rest. So basically it says A is being lost at 0.25 molarity per second. And right, A and B are being lost because the reactants are disappearing. A squared B is being gained because the products are reappearing. And so the question is, if B, oh, sorry, I did this wrong. If B is being lost at a rate of 0.25, so B is being lost at a rate of 0.25 molarities per second, A is being lost. Now, they're both lost, but because of this 2-to-1 mole ratio, twice as much of this is being lost every minute. So I need twice as much as 0.25 would be 0.50. And so that answer is C. All right, see if I learned my lesson. I have a hard time manipulating the screen using my finger, so you're going to have to wait till I walk over to my screen and go to 7. We just talked about this catalyst speed up reaction by altering the reaction pathway in such a way as to lower the activation energy. So what happens is, if this is what the reaction looks like with a catalyst, this, let me switch colors. This is what it looks like with a catalyst. So blue is without, green is with. The products and the reactants don't change. What changes is the hump to get over. They have totally different reaction pathways, but they start with the same reactants and end with the same products. It's just the middle is changed. All right, for a reaction, the kinetics is second order in X. So I would like to do this. For a reaction, the kinetics is second order in X and 0 order in Y. So this is what the rate law is. If the concentration of X is doubled, so instead of X here, I'm going to put in 2X. And the concentration of Y is doubled. Well, this is probably a dumb way to do it because X and Y are the names, but let's just pick numbers. Let's say on trial 1, this was 1 and this was 1, and now in trial 2, this is 2, and this is 2. The overall reaction will increase by a factor of 4. Why? Because 2 squared is 4. 2 to the 0 is 1. 4 times 1 is 4. So the answer is C. And a lot of what caused you guys a lot of pain and anxiety here was it's wordy. You have to really, especially on the multiple choice, sometimes you got to read them really slow and pull them apart a couple times before you can figure out what's going on. So here we go. Here's 9. For a reaction, the kinetics is second order in X and first order in Y, period. If the and so let's just do this. On trial 1, make them both 1. So this is K times 1 squared times 1. So this is 1K. And then X is tripled. So this is 3. And Y is doubled. So this is 2. And then just do the math. 3 squared is 9. 2 to the first is 2. 9 times 2 times K is 18K. Look at this. The rate went from 1K to 18K, so it increases by a factor of 18. That's E. 10, identify the intermediate. Now, here's what you do. When you add up the elementary steps, you add them together, canceling stuff that's on the left and the right. This cancels this. You end up with the overall reaction, which is 2NO. Do you see 2NO? It's nitrogen monoxide plus Cl2 goes to 2NOCl. So when you add up all of the intermediate steps, canceling off the things that are on the left and the right, you end up with the overall reaction. Now, the intermediate is anything you cancel off. Actually, the things that you cancel off are either catalysts or intermediates. The difference is catalyst is on the left-hand side in step 1, and it's regenerated on the right-hand side in the last step. Intermediates aren't there in the beginning and they're not there at the end. They appear in the middle and they disappear in the middle. So in this case, the intermediate is this. It's the thing you crossed off. C. All right. And by the way, guys, I'm just trying to explain it the way that I understand it. If you understand the answer and you do it a different way, I'm totally okay with that. Okay, so 11, 12. The overall order for this rate law is, now guys, the overall order is the sum of all of the exponents. So 1 plus 1 is 2. This is C. A reactant found in the balanced equation and not in the rate law is most probably found in the reaction mechanism after the slowest step. Now, this is kind of tough because I never really told you this, but remember, the overall equation comes from the sum of all the intermediate steps. The rate law, so the rate law comes off the stoichiometry of not the overall equation. The rate law comes from the sum of all the steps through the slow step. Because the slow step, the slowest step in a reaction is the one that determines the rate. And so if you have a reactant that isn't in the rate law, it's because to get the rate law, you add up the steps all the way down through the slowest step. When you get to the slowest step, you stop. The rate law comes from the stoichiometry on that. And if you have something in the rate law that's a reactant but is zero order, it's because it was found in the reaction mechanism after the slowest step. So when you added up all the steps through the slowest step, it wasn't there. That is a very tough question, but it's cool. All right, so I think this was actually a pretty short multiple choice test. We're almost done with this part. So when you get ready to study, because there's 6 big ideas, and I think big idea 6 might get broken to parts. But when you get ready to take your quiz on big idea number 4, make sure that you look at your original test and then look at the new test that you don't have yet and that you understand the problems. And then I spend a lot of time looking for some free response questions that are on the same topic, so you get used to looking at how they're worded, and make sure anything, the tests in class or the tests that I'm giving you or the free response questions that I'm giving you, make sure that you understand them all, because I will pick some randomly to test you on. All right, given the following reaction mechanism, identify any intermediates. What you do is you add up all the steps and you cancel stuff that are on opposite sides. And let's get the overall equation. I have a C on the left, a C on the right. I have a D on the left, a D on the right. So the overall equation is 2 A's. Oops, I got a B on the left, a B on the right. I got 2 A's and an E going to F. So 2 A's and an E going to F. So what are the intermediates? Now, I've crossed off B, C, and D. But 2 of those are intermediates, and 1 of them is a catalyst. Now, what's the difference between an intermediate and a catalyst? Catalysts are there in the beginning of the very first step, and they regenerate at the end of the last step. That means B is a catalyst. Intermediates aren't there in the beginning, they aren't there at the end, and they're in the middle, but they get crossed off. Because here's something that I don't think I hammered on enough this year. Either something is a reactant a product, an intermediate, or catalyst. Okay, these are the four things that people can be. If I look at this equation, A and E are reactants, F is a product, C and D are intermediates, and B is the catalyst. Identify the catalyst present. What did I tell you the catalyst was? B. Catalysts aren't there. They're there in the beginning because you got to put them in, in with the reactants. So you got to put them there in the beginning, but they're not a reactant or product, so they have to be regenerated. All right. Okay, here is I just did this one. The answer is E. I did it up above because this cancels this, and this cancels this, and this cancels this. You end up with two A's and an E on the left and an F on the right. So this answer is E. And then, I wonder, is that it? I think that might be it. Oh, it isn't. It doesn't like me. Come on. Come on. Don't be like that. Okay. Again, I just have trouble with that. I got to walk over to the computer. All right, 16. All right. This is an example of a rate law where you don't really need a calculator. So this is what I'm doing. First of all, do not bite on its fourth order with respect to A and second order with respect to B, because the stoichiometry does not come from the balanced equation. It comes from, you can get it by adding up the elementary steps through the rate determining step or the slow step, but most of the time you'll get it off a table. So what's the order with respect to A? You cover up A, you find a set of trials in which B doesn't change. So no change. This tripled. 5 goes into 45 9 times. 3 to what power gives you 9? This is second order. All right, I think that this is basically, oops, put the pen down. This is the same problem, same reaction. What's the order with respect to B? To find the order with respect to B, you cover up B, find a set of trials in which A doesn't change, no change, 1 and 3, this doubled, 2 to what power gives you 2, so this is first order with respect to B. All right. All right, now this is probably the hardest stuff in the chapter. And actually, I kind of want to talk about, if you look on your formula sheet, in the kinetics, there's only 3 formulas, but here's what you need to know for zero order kinetics. The equation you use, this is called the integrated rate law because we had to do an integral to get this, is the concentration, we say that A is a reactant of any time, the concentration of reactant A at any time is negative K T plus A sub 0. Think Y equals mx plus B. For first order, it is the natural log of A sub t equals negative kt plus the natural log of A sub 0. And for second order, it's 1 over A sub t equals positive kt plus 1 over A sub 0. Interesting. On zero order and first order, the slope of the line is the opposite of the reaction is the opposite of the rate constant, so the slope is the opposite of the rate constant. But second order, the slope of the line is the rate constant. It comes from the calculus. I will talk about that again now that everyone has had integrals. All right, so here's the deal. It says that the plot is linear when you plot the reciprocal of x versus time. And remember, we title graphs y versus x. So what order is it when this is the linear graph? And it's second order when that's the linear graph. Order means exponent. So this answer is C. All right, now it says a plot of A versus time is found to be linear. So this is A and this is time, and we get a line, and that means it's zero order. By the way, this zero order isn't on your sheet, but it's on the test. And I think what they're saying is if you are just using A's and T's alone and there's no function, there's no natural log, there's no reciprocal function, then that's a sign that it's zero order because nothing's going on there. Zero order. Okay, and then 20, the last thing. Okay, and I'm not going to try to overwhelm you in any given day. So what I'm going to do in a minute is just finish talking about this. All right, 20, an increase in the temperature of the reactants causes an increase in the rate of a reaction. So how come when you heat something, the reaction tends to go faster? The best explanation for this behavior is that as the temperature increases, the concentration of the reactants increases. That's not true. The only thing that happens when you heat something is that it moves faster and it collides harder. The activation energy decreases. That's not true. The only thing that makes the activation energy decrease is the addition of a catalyst. You didn't add a catalyst, you just heated it. The collision frequency decreases. Heck no, when things move faster, they collide more often. The number of collisions with enough kinetic energy to overcome the activation energy increases. That is the answer. And E, the orientation of the reactants is changed, so there are more effective collisions. That is not true, but I want to talk about this. There is something in biology called an enzyme, and there's a special kind of enzyme called a lock and key enzyme. And that's exactly what enzymes do, like a lock and a key. You know, when you put a lock in a key, it has to orient perfectly to undo the lock. What enzymes do is they hold one of the molecules that's in the reaction in the exact proper orientation so that when the other molecule runs into it, the orientation is perfect. This is what an enzyme does, and enzymes are catalysts. That doesn't have anything to do with temperature. Enzymes are what a biological catalyst is. They don't actually even lower the activation energy. Well, they do, because they just make the collisions more effective. You know, maybe one reaction, only 1 in 10 collisions is effective, and then when you throw an enzyme in there, now 1 in 2 is an effective collision, and of course the reaction goes faster. All right, now I'm going to flip back here. Now that you've had calculus, this is the last thing I'm going to do today because I'm a little nervous. Is this not recording? Is this not recording? Oh, yes, it's recording. All right. I saw it. All right, so, okay, so let me do first order first. We know that a first order chemical reaction looks like this. The rate, by the way, this A goes to B. So when I do this, just assume that A is the reactant. So first order means the rate is equal to K times the concentration of A to the first. Does that make sense? First order. Now, earlier in this multiple choice test, I had told you that you can monitor a rate of a chemical reaction one of two ways. Either how fast is A disappearing, or how fast is B appearing. And so because I have an A here, I'm going to monitor this as the rate of how fast A is disappearing. And how we write that mathematically is how fast is the concentration of A changing with respect to time. And why it's negative is because disappearing is negative. Okay, now you guys, most of you are in calculus right now. All right, this is called a separable differential equation. Why? Because I have A's and T's. So what I'm going to do is I'm going to get the A's on one side and the T's on the other side. So I'm going to slide this down, and I'm going to divide this side by A to the first, so they cancel. Anything you do to the left, you have to do the right. And, oh, I lied. Hold on. Do over. This is what I want to do first. Do over. A to the first. Okay, first thing I want to do is take cross products. So I get dA equals Ka to the first dt. And now I'm going to divide by A to the first. And so what I end up with, and I'm actually going to move the negative the other side just because I want to, you end up with dA over A equals negative K dt. What's the only thing in calculus that undoes a derivative? An antiderivative. Okay, so moving right along. What is the antiderivative of this? Oh, by the way, we're going to go from A equals 0. That's where you start, is the initial concentration, to A equals some time. And here we're going to go from T equals 0 to T equals some time. So here, okay. So what is the antiderivative of, you're used to it like this, dx over x. Pretend that the concentration of A is x. Well, you guys know that that's the natural log of A, evaluated from A sub 0 to A sub t. And then this is, what's the antiderivative? The constant goes up front. What's the antiderivative of dt? It's t, so this is negative kt. And that's evaluated from t equals 0 to t equals 1. And extend page. The ln of A sub t, it's the upper limit of integration, minus the ln of A sub 0 equals negative, sorry, this is t to t, kt minus 0, because we put 0 in. And so this is why you get this equation. The ln of A sub t equals negative kt plus the ln of A sub 0. So it looks like y equals mx plus b. So if you have t, time, on the x-axis, and the natural log of y, sorry, the natural log of the reactant, the concentration of the reactant on the y-axis, the slope of the line will be the rate constant, and the y-intercept will be the natural log of the starting concentration. And so that explains that one. And let me just do the other one quickly. Okay, so same thing. If you have a second order reaction, that means the rate So again, guys, we have A changing to B. The rate is equal to K times A to the second power. But again, you monitor the rate of a reaction by how fast A is disappearing. So it's the change in the concentration of A with respect to the change in time equals Ka squared. Just like last problem, I'm going to take cross products. Negative dA equals Ka squared dt. I'm going to get the A's on one side and the T's on the other. And I am going to move this negative just because I want to. And so you end up with dA. And I'm going to write it like this because you guys understand the power rule better if I bring this up. Equals negative K dt. And then what undoes a derivative, an antiderivative, and we're going to go from the concentration at time 0 to the concentration of whatever time you picked. And then this is going to go from time equals 0 to time equals whatever time you picked. And so what is the antiderivative of a to the negative 2? Well, you add 1. It's a to the negative 1 times negative 1, right? Power rule, you add 1. Negative 2 plus 1 is positive 1. Sorry, negative 2 plus 1 is negative 1. And then we're going to go from a equal the lower limit of integration is this, and the upper limit is this. And then this is negative kt, because the antiderivative of dt is t, from 0 to t. And then extend my page, and we get negative a sub t plus a sub 0 equals negative kt. And then I'm going to multiply everything by negative 1. So this is, sorry, this is to the negative 1, and this is to the negative 1. That's still there. Oh, so I'm going to multiply by negative 1. Holy mackerel. Let me just extend the page. All right, so this becomes a sub t to the negative 1, and this becomes negative a sub 0 to the negative 1. And then if I multiply both sides by negative 1, then this becomes positive kt. And then when I move this to the other side, I get 1 over a sub t, because that's what reciprocal means, equals kt plus 1 over a sub 0. And I just wanted you to understand those two formulas on the formula sheet. And that's enough for today, because if I look at this, I have been talking for 37 minutes. I'm done for today. What I want you to do then for homework tonight is I want you to take the big idea number 4 packet home and just read through it, because at the start of class tomorrow, we're going to take a test on it, which doesn't count. This is like if you took the AP test today, how would you score on this concept? Then we're going to grade them, and you're going to get some feedback on how you did, and then we'll go from there.